Hey everybody, and welcome back to Calc 3 Online. So today I just want to do some more examples with surface area and double integrals. We're going to do one kind of at the end that's a little bit weirder, a little bit harder. But to get started here, I just want to set up the double integral you would use to solve this following problem. So you've got this surface cosine of x squared plus y squared, and we want to find the part of the surface there that lies inside the cylinder, x squared plus y squared equals 1. So, if we think about the 2D part of that cylinder, right, it's just the circle, unit circle, right? And so we're just thinking of that extending out of the page and into the page. And the function that we're going to use in the integral is the cosine 1 right here. And so basically we're just setting up this double integral based on that circle, right? And it'll be a square root 1 plus that function squared or the derivative of that with respect to x squared plus the derivative of that with respect to y squared, and then dA. Right, so since it's a circle, I would personally do a polar. I think it's way easier. So we should convert everything to polar. So I'm going to start and just get my derivatives. My derivative with respect to x would be negative sine x squared plus y squared times by 2x. And then if you convert to polar, right, the x squared plus y squared part is nice because that'll just be an r squared. And then, we're just going to do that as my conversion symbol. We're going to get negative, I'm going to bring this in front too. So x is r cosine. So I'm going to have negative 2r cosine theta and then sine of r squared. And that would be the same thing in polar, right? And then we'll do f with respect to y. And we're going to get negative 2, I'm just going to put the y in front this time, y, then sine x squared plus y squared. So we go and convert that one, and we would get negative 2r now sine theta times sine of r squared. And then if we want to integrate over a circle, right, with a radius of 1, our dr ranges from 0 to 1, right, and the angle is the full 2 pi. So the setup would basically be 0 to 2 pi, 0 to 1, square root 1 plus each of these squared, right, which would be 4r squared cosine squared sine squared r squared, and then plus 4r squared sine squared the theta, and then I dropped a theta in here, and then sine squared r squared, and then we would do all of that, right, times an r dr d theta. And it's not actually horrible to integrate, but I don't really want to go through all that as well. The setup is oftentimes the hardest part in these problems as well too. So it's, I think, best to see the setup. But definitely I would do this one in polar, and there's nothing wrong about doing surface area problems with polar. Last time I think we just saw the rectangular one, but if the area is, a circular region, it's kind of always a clue that you might want to do the conversion to polar. All right. So this one I actually just want to solve out. So I want to find the surface area of the region that's described right here that lies inside this paraboloid, okay? And so to get started, let's figure out kind of what makes sense, what units make sense, and then figure out, whether we basically want to do this in polar or rectangular. So to do all that, I'm going to attempt to kind of draw this thing. So we have a paraboloid that is just going to be sort of centered there at the origin, like that, right? And we've got the part of a sphere that lies inside of that paraboloid, all right? And so, if we think about like intersecting, I mean, the reason this is a little tough to draw is that, you can see that you got z squared and 4z. So you're going to have to like complete the square to kind of know the equation of this sphere. And so it's not like one nice sphere that's just centered at the origin or something like that. So it's harder to draw, but you can imagine that if you're intersecting a paraboloid, right, and a sphere, there's no rectangular things going on really anywhere at all, right? Like, I'm just going to kind of draw a sphere here. But if you think about like intersecting these two things, the region is going to for sure be some sort of circular region. And so it begs that you should just use like polar and not rectangular coordinates. So that's actually what we're going to go ahead and kind of deal with first. So I do want, so this is a sphere that's going to go like above and below the XY plane, but we really only need to consider the part of the sphere like the upper half, right? So we really should complete the square and get the positive square root case in order to start kind of this problem. So if I move everything, so if I basically move this 4z over, right, I'm going to have b is -4. And so if I complete the square, right, what I would have there is plus z minus 2 quantity squared. And then in order to balance everything out, you'd have to add a 4 to that side, because that's what we added to this side to complete the square. So that's my sphere written in a more kind of normal form. And then if you solve for z here, you're going to get z is the square root of 4 minus x squared minus y squared plus 2. Really, again, plus minus, but we can just kind of consider the upper half of it because that's the only part where it's going to intersect the paraboloid. And so this is my function that I'm going to need to take partials of, all right? And it's not really a horrible thing to take a partial of, because the 2 is just going to disappear, and then the derivatives of this part look kind of similar. Just when you do the chain rule, you're going to have, a minus 2x on the top for one and a minus 2y on the top for the other one. And so it's very similar looking things. So if we do f with respect to x, we actually would also cancel, here, I'll write it right now. So I was just thinking that we would cancel the 2's even, because when you do the derivative of the square root, right, you're going to get a 1/2. But that actually would go ahead and cancel. And then when you do y, it's going to look very similar, except it'll be a y up top. And then square root 4 minus x squared minus y squared. So that is my my derivatives, right? And I will have to square those things. So if I go ahead and do, well, I think we'll just go ahead and plug some of this in now. So if I square f with respect to x, right, you'll have x squared, and then the bottom would just be killing the square root. So you'd have 4 minus x squared minus y squared. And then likewise, if you do f with respect to y squared, you're going to get y squared over 4 minus x squared minus y squared. And we know we need a 1 in here, but just to make things a little bit nicer, I can put the 1 in as 4 minus x squared minus y squared over 4 minus x squared minus y squared. And that way I get common denominators, right? So this is kind of where my my double integral starts popping up now, and this is where I would want to start simplifying things and then start thinking about converting to polars, how I would do it. So if you look at it, it's pretty nice actually, because if you combine these fractions, you have a negative x squared and an x squared, which is nice. Then you have a negative y squared and a y squared, also nice. So really, the whole double integral there reduces down to square root of 4 over 4 minus x squared minus y squared, and then dA. So this is about as simple as we can get it right now. So this is where I would start thinking polar. All right, so to do that, we need to intersect, I'm gonna get rid of my bad picture here a little bit. We need to intersect these two things to kind of see, what the 2D region of intersection is, right, in order to figure out our bounds. So you've got to basically set up a system here, and I'm just going to do substitution to see where these intersect. So this is kind of nice because z is x squared plus y squared, so I can pop a z in here, right, in place of x squared plus y squared. Then I have plus z squared equals 4z. And that's just like a nice quadratic, right? I can solve set equals 0, get this, and then factor out a z, get z minus 3. And then you can see that z can equal 0 or 3. And so this is nice because z is equal to 0 or 3, which means that x squared plus y squared is equal to 0 or 3, right? And so that means that the radius, right, because this is r squared, is equal to 0 or 3. So we now know that in r is going to be equal, r squared is equal to 0 or 3, or basically the radius runs from root 3 to 0. And so that's nice to know for this part, for the radius. And then for the angle, it's it'll be 0 to 2 pi because this paraboloid, right, is centered perfectly at the origin, so it's going to go around, the full 2 pi from that part. So you have a full 2 pi because of the paraboloid being centered at the origin, and then you've got your radius running from 0 to root 3. So you should be able to now go and substitute those things in for polar here. So if I convert this thing to polar, 0 to 2 pi, 0 to root 3, then square root 4 over 4 minus r squared, right, because minus x squared minus y squared. And don't forget you got an extra r there, r dr d theta. And then now you can finally do an integral, right? So what I would do to get started here, if you do u equals 4 minus r squared, right, you're going to get a 2r derivative kind of thing popping up, which means that we could use that for I see the r here, so I'm going to do a u sub, basically. I see the derivative of this somewhere else, which means I do u sub. So let u equal 4 minus r squared. Du is minus 2r dr. So then negative a half du is r dr, which is what I've got right there. And so we go, and this is another one too. There's nothing here that has to do with the angle. So really I can just scale it by 2 pi. So I'm just going to do that. 2 pi times, I'm not going to do u bounds. Square root of 4 over u. And then I also have to divide by negative 2, actually, from my du in here. So then that part's all good. I would just have du. All right, and then this is actually pretty nice because I'm going to cancel these 2's here, right? But then I take the square root of 4, right? Make that a 1 now, right? Which I guess I'm going to write it actually this way. And then the 2's had canceled, but then I brought a 2 out because I took the square root of 4. So really now in front I have minus 2 the pi still. So then you can just do a nice, it's just a power rule, really, right? So you get minus 2 pi times u to the 1/2 over 1/2, and then we're going to plug in u equals 4 minus r squared. So you get minus 2 pi times 2 times 4 minus r squared to the 1/2, and evaluated from now 0 to root 3. And it's all fairly straightforward stuff from here. I'm going to let you finish that thing on your own if you want to see how it all works, but you should get 4 pi. So I think this one's kind of neat because it uses like a lot of tricks. It uses, first off, just trying to figure out even what the region would look like is kind of tough. You have to deal with some kind of clever trickery maybe in here to get that algebra to be nice so you can get it to this form before you go and start doing polar. To get even the region, to know that, you have to think of the intersection part in this algebra. So this is a lot of algebra in this problem. It's a good one to know. All right, I want to do one more here. So this figure below shows the surface you get, this one, when the cylinder y squared plus z squared equals 1 intersects the cylinder x squared plus z squared equals 1. It's kind of like a beach ball looking thing is sort of how I think of it, right? So if you think about two cylinders, intersecting that go right through, parallel to the axes that they run down, you're going to get this. I don't think it's kind of too hard to see that. But there's a lot of tough questions that basically you can ask about these sort of things. And one that we can ask is find the area of the surface. All right, so it's a little hard to kind of visualize what's going on maybe. So let me sort of clear this up a little bit. So this yellow cylinder here that is running that way, if we do think our axes go this way, x, y, z, then the yellow one, right, would be this one, because it's the one that x is allowed to be kind of free and range through all the values there. The blue one then is this other one here, and it's almost easier to think about what it kind of would look like in the XY plane, I think. So you can see, one of the important things, I guess I just want to point out, these intersection kind of lines that you get right here and here, where there's going to be sort of like a crease from those intersections. Those are truly going to be, because, these are perpendicular. That's going to be right in the middle between the two axes. So there's a y equals x kind of intersection line, and also a y equals negative x intersection line. And that's, this crease here is the y equals x one, and this one, it's kind of hard to show, but that crease back there is the y equals negative x one. And this thing is, one of the nice things is that it's, symmetric above and below. So the surface area above should be the same as the surface area below, based on these equations, right? So it's one of these problems where I would probably just go and do half of the surface area and then double it at the end. So if I take like this right here, if I solve for z, right, 1 minus x squared, then I just take square roots, right? You're going to get plus or minus square root of 1 minus x squared. So we can just work with the positive one and let that be my function of x and y that I'll take derivatives of. And then we just know that by doing this, we're going to have to double our answer, whatever we get. So let's take a derivative. We're going to need that for surface area. We're going to get, with respect to x, we'd have negative 2x over 2 square root 1 minus x squared. So again, kind of like the last problem, those 2's would cancel. It's nice actually, f with respect to y is just 0, right? There's nothing in here that has to do with y, so the derivative with respect to y is 0. And then if we go to kind of start setting up an integral, we have to plug in this squared and this squared. So we're going to have x squared over 1 minus x squared, then like plus 0, and we need a 1 in here too. So I'm going to do the same thing I did in the last problem where I put the 1 in with common denominator as the other kind of messy expression here. So plus, and then dA. And then this is nice again. So this and this would cancel, right? So really my double integral that I'm kind of working with is square root. No, I don't even need big square root. I can just do 1 over square root 1 minus x squared dA. All right, and so now kind of back to here for a second. So this kind of triangular stuff, right? You can make this a really nice rectangular coordinates problem, right? If you think about, you're going to have some surface of, some area of the surface above this part, this part, this part, and this part, right? Kind of like the different colors here. And the, you can, in a sense, because of all the nice symmetry with these 4, you basically can do, we've already split the problem in half by just thinking about what's above the xy plane, but I'm actually going to go even further. I'm going to say, let's cut it off like here, okay, at, kind of the boundary of one of these right here. And then I'm actually going to just find the surface area above like a triangular region like that. So one that'll go from negative x to x. And then I'm going to have to multiply by, I'm going to have to times by 4, right? Because there's one of those here, one of those here, one of those here, one of those here. And then don't forget that because we did the plus and minus thing, I will also have to multiply by 2 more, all right? So kind of 2 different reasons I'm doing that. This is just because of symmetry above the plane, and then this is above or below the plane. I guess I should also say, since these cylinders are equal to 1, right, they're, I didn't really tick this off in the picture originally, but, this would go out to 1, right, yeah, we'll just leave it like that. So that purple line is at 1, right, because it's going to be a radius of 1 cylinder. So this is as far out as it goes. Okay, so setting all this up, this double integral, much easier to do a dy dx. So that's where I'm going to start. Doing a dy first means we're going to go from this diagonal to this diagonal. Right? We're going to go up like that. So negative x to x. Then in terms of left and right boundary, you go 0 out to 1, right? Again, because the radius is 1. And so I'm just trying to think about what color. I'll just do green again. 0 to 1. And then we have 1 over square root 1 minus x squared dy dx. The dy integral is really nice. We would just have 0, 1. We would basically just get a y to pop up, right, in here with the dy integral. Then we're going to do x minus a negative x, so we're going to have minus 2x. So we have minus 2x over square root 1 minus x squared dx. Another u sub problem. Just let u equal 1 minus x squared. Du is minus 2x dx. I just realized I don't know why I put a negative there. There's no reason for there to be a negative. Get rid of that. You just literally, for that integral, you're just doing y. You're getting a y, and then you're doing x minus negative x, so it's positive 2x. I don't know. Anyways, so it's not really that bad. I'm going to skip some steps here because I think you can do this part. So you basically will get, when you evaluate everything here, you're going to get 2. Okay? And if you're having trouble with those kind of things, I'm happy to go through it, but it's really, it's not too bad if you've kind of already seen this one too. So now I have to kind of go back and do a bunch of multiplications to make sure I account for the full surface area. So 2, basically what that represents is, I'm going to try and draw it here. So it's like the, here we'll do, so it's like if I cut that chunk sort of out, okay? This thing right here, this blue kind of part above the XY plane, that thing has surface area of 2. And that's what I just found sort of above here. Actually, exactly that one, because it's the one that spans over the x-axis like that. So you have to multiply, you have to do that, here also, right? And you get like that kind of another chunk of 2, and then there's one in the back over there, another one in the back over there. So that's why we're multiplying by 4. So we times, here we'll do it like surface area in total equals my 2 times the 4 across the top there, and then times by another 2 for this part up here, right? And so this is the kind of math that I always mess up. I believe that's 16. There we go. So that is the surface area of that really weird thing that kind of looks like a beach ball. That is the intersection of those 2 unit cylinders.